In the last video, we talked about vision language models and how they work and everything like that. And today I'm going to be sharing some research I've done that dives deeper and everything builds upon where we were. So as a quick recap, we talked about this vision tower concept that lives alongside our language model. And the vision tower's core role is to translate visual information into representations that our language model can understand. And in the last video, we explored how interpretable these image tokens actually are by directly unembedding them or taking them and projecting them through our language head. And there was some interesting stuff there. We saw that at least some degree of semantic interpretability is there. Gemma 3, which I've been using for this research, outputs 256 of those image tokens from its vision tower. And so, kind of from the start, I've been really interested in trying to interpret how the model actually utilizes those 256 tokens. And one of the ways I've been conceptualizing it is as like 256 tokens of budget, where we kind of have these different slots, and our goal is to encode information in a way that our language model understands. How are these slots actually used? Are there certain ones that are more meaningful than others? Is meaning very distributed? Is it very specialized? Do certain slots carry certain location meaning? Stuff like that. So I went digging to see what I could find, looking for any weird token slots, and 193 totally jumped out to me as being exceptionally weird. And so kind of this video is going to be diving into how I found out that 193 is weird and what I know about it, and kind of leaving the door open for the mystery that I still don't fully understand exactly what it does. Let me tell you about the data set. So I pulled 10,000 images from Google's Open Images version 7, and I processed them by putting them through Gemma 3's Vision Tower. And so each image gives us 256 embedding vectors. And these are those image tokens, but I've more so been seeing them recently called soft tokens. But same thing, these are what's getting fed to the language model. And so I stored all of this in a database where we have our 10,000 images and all the embeddings. And here is a sample of 8 of these images from this data set. So it's not a huge data set, but I think it's statistically large enough that we can draw some real findings from it. So I want to know if there's any interpretable structure in how information is encoded across our 256 slots. And so I began by just looking at one image and computing a pairwise similarity across each slot. So for that, I mean, I want to know how similar the vector is in slot 0, how similar it is to slot 1, and 0 to slot 2, and so on. So that gives us a 256 by 256 similarity matrix, and I use cosine similarity there. And so that kind of tells us how similar are the different slots to each other. And so I ran that for our 10,000 images, and that gives us our similarity tensor of this dimension. And then I was like, well, if we average across our 10,000, then if there's any structure there that is not content specific, we should see it emerge. And so that is what this plot is really looking at. And as we talked about, 193 stands out as being the most dissimilar to everything else. So yeah, this plot tells us that 193 is very unusual. Everything else is pretty much within a pretty similar band. Obviously, this is our identity diagonal, um, but everything else is kind of largely within this similar range to each other. There's interesting structure here going on, but 193 far and away the darkest. And so I wanted a little more descriptive version of this to see how, um, like, which of these positions are actually the most dissimilar. And so I made this plot, and the mean here is 0.59. And so, like I mentioned, a lot of these tokens are kind of within that same range. And we really only have like a couple handfuls of weird outliers. And we can see 193 very drastic compared to everything else. But yeah, so that was interesting. And so this tells me that because 193 is so dissimilar to everything else, that 193 must be encoding something pretty unique compared to all of the other slots. So I wanted to know how consistent this was across images. And so to calculate that, I looked to find for each image which slot is the outlier. And far and away, 193 is the outlier, where outlier means the least similar to everything else. And interestingly, there's only a handful of tokens that ever appear as outliers in our data set. But yeah, 95% of our data set has 193 as the outlier. So that tells me something weird is going on there. So I next wanted to know if this token 193 weirdness persists if we rotate the image, because maybe 193 was something about the image content. And so if we rotate it, maybe that won't hold true. And so I ran it for a couple of examples. We can see 193 is the outlier regardless of our orientation here. Same here and here and here. Interestingly, we have an example that breaks our idea. We see 48 here. So this is a image of a code snippet, and 48 is our outlier. And 193 looks pretty normal there. So that is interesting. And then another example of maybe a non-natural image. We have this diagram, and 243 shows up as the outlier neutral, and then when we rotate it, we see 48 as our outlier. So kind of what this tells me is that the outlier position seems to be largely rotation invariant. For our relatively small sample size, the vast majority of cases hold that our outlier does persist over rotation. And we also learned that there are examples where our outlier is 48. And interestingly, if we were to go back here and look at our plot of the most dissimilar positions, we see 48 and 243 show up as second and third in our ranking. So we kind of have seen that there are these outliers, and I was interested in trying to understand what they encode. And I wanted to know how similar the outliers are across images. And so by that, I mean, in our first notebook, we looked at within one image, we saw that 193 is by far the most dissimilar slot. But If 193 truly does encode some type of meta information, then across the images where 193 is our outlier, then 193 slot should actually be very similar across all of those things. And so I tested just that by getting the bucket of all of our images where 193 is the outlier, as well as 48. And so just to show that, 48 seemingly is a little bit different. Maybe there's a slightly more textual information going on here, but it's not immediately clear to me how the different content would shape our outlier. But anyway, I calculated that cross image similarity. So looking at the slots, how similar they are across our images. And interestingly, this is more or less a mirror of what we saw as the dissimilar per image. So 193 is very similar across our bucket where 193 is the outlier. And then we recognize things like 48 and 243 as well. So yeah, very interesting stuff here. I think that this plot kind of tells us 193 does in fact have a pretty good chance of encoding some type of meta information because each image's 193 slot is so similar to each other one. So at this point, we've defined 193 to be weird. We noticed it's an outlier within images, it's consistent across images, and it's largely rotation invariant. And so the natural follow-up question is, okay, what is it actually encoding? How can we interpret it? And so I began by computing the 193 direction. So I wanted to compute the centroid of our position 193 embeddings where 193 is the outlier. So that pretty much gives us like the shared direction, or like essentially like 193-ness. It's what those embeddings have in common. And so taking us back to the first video, I was wondering if we could just unembed it. And so when we unembed that centroid, unfortunately, whatever 193 is encoding, it doesn't really seem to align with the model's textual vocabulary well. We're not really getting anything semantic, and all of these probabilities are very low. So this doesn't really tell us much. So if we can't read what our 193 encodes, can we understand what it does by manipulating the model? So to do that, I kind of have 5 different prompts across different areas that are meant to kind of represent different VLM use cases. And we have our test image of the L in Chicago. And so I began by doing a zero out ablation. So if we, before the language model receives our 256 visual soft tokens, what if we take that 193 one and just zero it out? What happens? So interestingly, we can see like our baseline response compared to the zero out position. And interestingly, these are almost identical responses. And the same is pretty much true for everything, for all of these different cases. So I was kind of surprised by this. I would have expected zeroing out to break the model more. but I was curious to try something else, and so kind of inspired by the Golden Gate Claude work, I wanted to do some like directional steering, and I wanted to do so by seeing what happens when we flip the direction of our 193 vector to see if there's kind of like some polarity going on. And so when we run our same prompts against this, we can see that this does kind of break the model. And, it's able to see the image here, as we can tell by its response, but it's not actually answering the question in this case. Our description is kind of seems to work, but our visual question answering, this is a garbage response, obviously. And this is an interesting hallucination. This photo was definitely not taken on this date. And then when we ask it to list 3 things, it goes back to describing what it sees. So we found that 193 is really weird, but it's not interpretable by doing our unembedding technique. Zeroing out doesn't actually break anything, which was a surprise. When we flip the direction, that does actually break things, and I think we would need to do a larger sampling to figure out kind of more rigorously what the failure modes actually are. But just from our little sample size, I think like we can tell that the model is still seeing the image, but it kind of seems to lose its ability to like answer the question. So unfortunately, I'm not in the place to make a strong conclusion from this, but I think we have made a strong case that 193 is pretty weird. And like I mentioned earlier, I would love if anybody is able to build upon it, and kind of take it to the next level to actually interpret the weirdness that's going on. That'd be awesome. Please reach out to me, and all of this code is on GitHub. The link will be in the description. But yeah, thank you for watching. If you like stuff like this, you're in the right spot. I've got more videos like this and more on the way. So thank you.